Good morning, students. So, in the last class, we have seen Christian Huygen's wave theory, and in this class, we will try to use these theories to Christian Huygen's principle or wave theory to derive the law of reflection of light and also the law of refraction of light. So, let us see how we can apply this Huygen's concept of wavefront to reflection of light. What is the law of reflection of light? We know that according to law of reflection of light, the angle of incidence should be equal to angle of reflection. So for reflection to occur, we need a mirror. So let me consider a mirror. Is this straight to you? So Mn is a straight mirror. In order to show that it is the upper surface that is reflecting, let me put these dashes here, which means this is the rough surface. Reflection takes place on the upper surface. Now, let me assume that two parallel beams of light are coming at the same time and are incident on this mirror surface. So, let me assume two parallel beams starting from this point. They are parallel and they are coming obliquely and hitting on the surface of this mirror. So let one ray of light come and incident at a point A. So at the same time, suppose the light comes from here and reaches here in time t1. In t1 time, it have traveled through this much distance. Let c be the velocity of light. So this distance will be ct1. So in the same time, the parallel ray must have traveled and must have reached only till here. So these are two parallel rays coming. So they started off at the same time. And in time t1, it have traveled this much distance, and time t2, this light must have traveled this much distance and reached the point D. So at time t1, the light have traveled and have reached this point A, which is incident on that, and at the same time the light from this point have traveled only till the point D. Okay, so this distance is T1C. Is this much clear to you?
Yes, teacher.
Okay, now after T1, let us consider another time interval T2. What happened to the light which is incident at this point? When it touches the mirror, it will reflect. So let me draw a normal here. So the light which have touched here in time t2, if this is the angle of incidence I, with the same angle of reflection, it will get reflected back to the same media. Let that time be t2. In time t2, it has reflected back. Let c be the velocity of light. Now at the same time t2, the light which reached here didn't touch the mirror, so it will pass on straight. So it will pass on straight. So in a time t2, ct2 is the distance traveled by light from the point D, and it will reach here at the point B. So in the same time t2, the light that reached D continued its travel and reached the mirror at point B. And the light that reached A will get reflected back. Okay. Now we have when the light reached A, that is in time t1, when you draw a wavefront, it is perpendicular to the rays of light. So here we have, this is the point D. Here, this is the incident wavefront. Because these two are the incident waves, right? So the line which is perpendicular to the two incident rays of light is the incident wavefront. We learned that wavefront is always perpendicular to the light rays or the direction of propagation of the light rays. Now, after time t2, the reflected wave have traveled this distance and this wave have continuously traveled this distance. We don't know until which we have to stop. So what we have to do while actually drawing this diagram in your paper, you have to take the compass and measure this distance, CT2. So CT2 distance will be traveled along this reflected wave. So since I don't have a compass at hand, I'm using my fingers. So this is the distance, same distance you have to take and draw an arc. So you got this point. So this distance is again CT2. So here, let me mark this point as E. Now, this is the reflected ray, right? So at this point, reflection will start here. At this point, reflection will start here. So I can consider a perpendicular drawn from here to here as the reflected. This is the incident wavefront, and this will be the reflected wavefront. Is it clear how I constructed this diagram?
Yes, teacher, got it.
Okay, so this is the incident wavefront and this is the reflected wavefront. Now the angle of incidence is I here. Angle of incidence between means the angle between the incident ray and the normal. We know that the incident ray and the wavefront are perpendicular, normal and the surface are perpendicular. So the angle between the incident and normal will be same as the angle between the wavefront and the surface. So this angle also will be equal to I. Similarly,
Teacher, can you say again?
see, the incident ray is perpendicular to the wavefront, which means this incident ray, let me consider this as A, B, C, D, E, F, G. Okay. FA is the incident ray. It is perpendicular to the wavefront, that is AD. Okay. So these two are perpendicular to each other. Similarly, the normal N1, N2. This is the normal. And this is the surface Mn. So normal N1, N2 is perpendicular to Mn. Right? So the angle between the incident ray and normal, that is angle between FA and N1, N2, will be equal to angle between these two lines, that is AD and MN. Is that clear
Yes,
now?
teacher, got it.
Okay.
Yes, clear.
In the same way, R is a reflected angle, right? Angle of refraction. That is the angle between, if this light get reflected, then also angle between the normal and the reflected ray. So with the same explanation, we can tell the angle between the surface and the reflected wavefront also will be equal to R. Because the reflected ray and the reflected wavefront are perpendicular to each other. Similarly, the normal and the surface are perpendicular to each other. So the angle between the reflected ray and the normal will be same as the angle between the reflected wavefront and the surface. So this angle will be equal to R. Now, our aim is to show from this figure that I is equal to R. To show that, consider the triangles, this one containing I, ADB. ADB. Consider triangle ADB. Let me draw that separate here. ADB. This is A, this is D, this is B. We have this angle I and this is the surface. Okay, and then we have this dB is equal to CT2. We know this much. So this is ADB and this is the incident wavefront. This is one triangle. And consider the triangle, this one containing R, that is BEA or ABE, this triangle. Consider ABE. So I am drawing ABE here. This is AB, mirror part, and then E, ABE. ABE. So this angle is R. This angle ABE. So let me consider triangle ADB and ABE. These two triangles. ABE. Okay, we have two triangles. Now, from these two triangles, they have a common side, AB. So AB is equal to AB. One of the sides are equal. AB is equal to AB. Now, we know that this distance is CT2. We measured the same distance here and drew a arc and we have got the point E. So, AE is also CT2. So, these two distances are same. So, from these two triangles, we have one side equal. We have another side also equal, which means from this triangle, BD is equal to AE, which is equal to CT2. So, two sides are equal, right? And what is this angle? Angle between the wavefront and the incident ray? 90 degree. And the angle between the reflected wave and the reflected wavefront, that also should be 90 degree. Always the ray of light and the wavefronts are perpendicular to each other. So this angle is 90 degree and this angle is also 90 degree. So the third point which we got is angle D is equal to angle E, which is equal to 90 degree. So we got three conditions. What does that make these two triangles? If two sides and an angle are same, what do you call those triangles?
They are similar.
They are similar or congruent triangles, right? So for congruent triangles, their angles should be same. So I will be equal to R. Is that clear?
Yes, teacher.
So from these two conditions, we can say that these two triangles are similar. Therefore, angle I is equal to R. I is equal to R, which means the angle of incidence is equal to angle of reflection, which is the law of reflection. So, considering the wavefronts, we can get to the law of reflection. That is why we say that Huygen's principle can explain the reflection of light. Is this clear to you?
Yes, teacher. Teacher, do you have the textbook?
Yeah, I have the textbook with me.
Can you take page number 440?
440, 440. Okay, let me take. Yes. Yes. Page number 440.
See,
Yeah.
as figure 7.5.
7 point.
The same.
7
5.
point. Yeah. In textbook, this figure is not very clear. They have shown the arc at a different point. There is slight difference. I think this is a better way of
And even the rate, their R is bigger than the I. I mean, refraction.
Yeah, that is
For the
why
first.
I told forget about that figure. That figure is not clear enough. The PowerPoint which
Okay.
I will be sharing you have a better figure like this. So this is the right way to construct. So the figure which is given in your textbook is not appropriate. That R is double the size of I. So it doesn't make sense, proper sense. Okay. So don't consider that figure which is given in your textbook. This is a better one. And this figure I am sharing you in the PowerPoint as well. Okay. So let us consider now how Huygen's principle can explain refraction of light. So the procedure is similar. If you understand this part, how it can explain the reflection of light, with some difference, we can consider the refraction of light as well. Do you remember the law of refraction? Refraction of light. What is meant by refraction of light?
Sin I by sin R equal to constant.
Sin I by sin R equal to constant. Yeah. What is that constant?
A refractive index.
Refractive index of the second medium with respect to the first medium. So suppose there are two medium, because for refraction to occur, there should be two different medium. Refraction means when light enters from one medium to another, it bends at the surface of separation. If the second medium is denser, it bends towards the normal, and if the second medium is rarer, it bends away from the normal. So let us consider two medium. Let this be medium A and this is medium B. Let us assume that medium B or the second medium is optically denser than the first medium. Optically denser means the light will have a lesser wave velocity. Means light will travel slow in medium B compared to medium A because this is optically denser. According to Snell's law of refraction, sin I by sin R is equal to mu BA, which means refractive index of B with respect to A. Let us see whether we can find this equation considering Huygen's principle. Okay, so let me first construct the diagram which is similar. So like before, I assume two parallel rays of light coming and meeting the surface. So let one ray of light come from here and reaches the point. Let me mark it as A on the surface. So at the same time, let this light ray come and reach here in a time t1, and let C1 be the velocity of light in this medium, and let C2 be the velocity of light in this medium. Okay, so here the distance travel will be C1 T1 when it reaches and hits at point A. Now another parallel beam of light will be coming and hitting, coming towards the surface, but in the same time T1 it will reach only a shorter at a point D. So it will have traveled a distance C1 T1 here and have reached only this point D. So these are two incident light rays. One reaches B and one reaches D. Now after time T1, let us consider another time interval T2. In T2, the light that have reached A will move to the second medium. So this is denser. If this angle is I, what about the angle of refraction? Will it be equal, greater or less?
Less.
Less. It will bend towards the normal because this is a denser medium. So it will travel like that with R less than I. So this is the refracted ray. But at the same time, the light ray which have reached here is traveling in the same medium, right? So at that time T2, let the light ray continue its path in the same medium and it must have traveled C1, T2 here the same time. Okay, but we know that C in this medium it will travel with the velocity C2 which is less than C1. So it will have traveled a distance C2T2. C2T2 which will be less than C1T2 in the next time interval. So if this is C1T2, how will I draw the arc? I have to take on compass C1T2 distance and reduce a little bit. Okay. For reflection, what we did, we took the distance on compass and we took the same length and marked the arc. But here we know in the second medium, it will travel a little lesser distance because the velocity is less. So I will take a compass, measure this distance and put a little bit less and draw a arc here. So I will get an arc here. And this distance is C2T2, which is less than C1T1. See, C1T2 is this much. C2T2 will be little less than C1T2. Now, at this point, it will continue for refraction. So here, when I draw a line from here to here, I will get the refracted wavefront. And from A to D, I will get the incident wavefront. So this is the incident wavefront. And here I have got the refracted wavefront. Is this clear how to construct that? It is similar to reflection of light, but here what we are doing, it is refraction. So it is going to the second medium, but the speed of light is less. So the distance we have to reduce a little bit. That's all. Is this construction clear to you? Can I go for the derivation?
Yes, teacher.
Okay. Now this angle is I and this is R, right? So this angle is I means the angle between the incident ray and the normal. You know that incident ray and the incident wavefront are perpendicular to each other. Similarly, the normal and the surface are perpendicular to each other. So I can mark this angle also as I. The angle between incident ray and normal will be same as the angle between the incident wavefront and the surface. By same explanation, I can tell the refracted ray and the normal. Refracted ray and the refracted wavefront will be perpendicular to each other. And the normal and surface will be perpendicular to each other. So the angle between refracted ray and normal will be equal to angle between the refracted wavefront and surface. So this angle will be equal to R. Is that fine? Now let me mark
Teacher,
this form. Yes. Okay.
Sir, I have doubt in this one only. Like how you took R, both of them angle R.
This is the angle of refraction, no doubt about it, right?
Yes.
R means the angle between, R is the angle between normal and refracted ray. No doubt about this, right? Angle between normal and refracted ray. Now I am marking here the angle between, instead of normal, I am taking surface. And instead of refracted ray, I am taking refracted wavefront. Normal and surface are perpendicular to each other. And refracted ray
Yes.
and refracted wavefront are perpendicular to each other. So the angle between normal and refracted ray should be same as that between surface and wavefront. The same way we consider here. Angle between incident ray and normal is equal to angle between incident wavefront and surface. They are perpendicular, which means we are rotating them, the whole arrangement through 90 degree. That's the only difference.
Yes,
Angle
teacher, got it.
between normal and the incident ray. If this arrangement I have rotated through 90 degree, I will get the same thing.
Okay, okay.
And this is
I got it
the
now.
angle, refracted ray, right? Normal and refracted ray. So if I rotate the whole thing through 90 degree, what I will get? Oh. So if I rotate the whole thing through 90 degree, I will get that with the surface and the wavefront. Is it okay? Does that make sense to you?
Yeah, teacher, got it.
So that is why I mark this as R. Now let us consider the triangles. So let me consider triangle ADB. From triangle ADB, I have sin I is equal to, I'll go fast, opposite by hypotenuse. This is 90, this is 90. So the AB is the hypotenuse. Opposite side is BD divided by hypotenuse is AB. So BD is equal to C1T2 divided by AB. Similarly, sin R is equal to, from triangle AB, oh, I didn't mark a point here, E. So from triangle ABE, sin R is equal to opposite side by hypotenuse. Opposite side is what? AE divided by hypotenuse is AB. So AE is equal to what? C2T2. C2T2 divided by AB. So if I take sin I by sin R, I will get sin I by sin R is equal to C1T2